Good, fantastic. So, obviously our data comes out slightly different because it's experimental data. Let's get rid of this. So I just did that as an example, okay? Let's get rid of this and let's recreate our probability distribution using these parameters, okay? So we've still got x and we've still got the probability that x comes out. So x, remember, is our outcome. We can either have 0, 1, 2, 3, 4 or 5. Those are our different outcomes that we can have. If the probability of success is 0.6, we want to work out what is the probability of x equals 0. So what's the probability of getting no successes? What's the probability of getting 1 success, 2 successes, 3 successes, 4 successes, etc., etc., etc. Okay, using these parameters. So we need to come up with a way of finding the relevant probability. Okay, so have a think about this. What would the probability that x equals 0 be? Okay, so what does this mean, first of all? What's the probability x equals 0? What does this mean? Put it in words for me.
It fails 5 times.
Exactly, so none of those 5 times result in a success. In other words, you miss every single time you throw that beanbag. Okay, so you can illustrate that graphically like this. Okay, now if you think about it, I said that the probability of getting it in the beanbag was 0.6. So what's the probability of not getting it in the beanbag? Absolutely, 0.4, right? Because it's got to be complementary, right? So what I'm literally saying there is I'm getting 0 successes 0 times. Does that make sense? Because if it's not landing at all, like look at the screen, if it's not landing at all, I'm getting no successes. So therefore, the probability of success is 0.6, and I'm having that 0 times. So it's 0.6 times 0.6, 0.6, but I'm not doing it any time, so it's 0.6 to the power of 0. Does that make sense? Okay. But then I'm also doing then all 5 successes. So it'll be 0.4 to the power of 5. Is that clear? So no successes, in other words, 0.6 to the power of 0. And every single one is going to be a failure. So it's 0.4 to the power of 5. Okay? So you then need to think, how many times can you do this? Now, this isn't really that interesting at the moment, but you remember with the last theme that we did, the number of times that you can get no successes from 5 trials. Okay? Number of times you can do that is just 5C0, or just 5C0 like that. Does that make sense to everyone? So you need to think, how many successes are you having? How many failures are you having? And how many times can you get that many successes from that many trials?
A question. 0.4 means failing 5 times?
Yes, absolutely.
Or not by single.
Okay, so 0.4 is the probability of a failure, and you're doing that 5 times. So it's 0.4 times 0.4 times 0.4 times 0.4 times 0.4. Yeah, so 0.4 to the power of 5. Okay, and you're getting no successes, so it's 0.6 0 times, 0.6 to the power of 0. Is that okay? Yes. Yep, good. And then you just need to think, how many times are you getting 0 successes from 5? Hence, it's 5C0. Is that okay with everyone? Does that make sense? So there's 3 things you need to consider when you're doing a binomial probability. You need to consider the number of times you get that success, the number of times you get that many failures, and the number of ways of getting that many successes from that many trials. Is that okay?
When you times 0.4 to 5 times, it equals this.
Yep, that's fine.
Then it's not 0.
Do you remember that our one, because we did our experiment, it just so happened that nobody got 0 successes.
So it's not real.
In our particular example, but that's because ours was experimental. In reality, if you should have this, what you're saying is the theoretical probability should be about 0.1. Yes, about 1%. Okay? Just remember that because we said that our sort of situation wasn't that reliable, what I'm now saying, to make it a little bit cleaner, let's suppose that probability of success was 0.6. What then should be the expected number, or what's then the probability of getting 0 successes? Is that okay? Yeah, okay, good. So let's have a think about the probability that x equals 1. Okay? Probability that x equals 1, how many successes are we having? 1 success. Okay? So in other words, I could represent it like this. Okay? So 1 success and then the rest are failures, so 4 failures. Okay? So if there's 1 success, I'm going to have 0.6 to the power of 1. 1 success. Yeah, the probability of success is 0.6. I'm going to have that to the power of 1. How many failures have I now got? Good. So it's going to be 0.4 to the power of 4. then the only thing to consider now is how many ways I can get one success from 5 trials. 5, choose 1, exactly, which is 5. Does that make sense? So this thing over here is always done from the perspective of the success. Is that okay? It's always done from the perspective of the success. Okay, let's go through the next one quickly. What does the next one say? Probability that x equals 2? 2 successes. So therefore it's going to be 0.6 to the power of 2. 0.4 to the power of 3, because there's going to be 3 failures. And then how many ways can I get 2 successes from 5 trials? It's going to be 5C2. Yeah, 5C2. Okay. Can you see the reality? Can you see what's happening here? If I want to generalize this, so if I want the probability of getting R successes from n trials, yeah, so it's going to be NCR, because I'm saying that many successes from that many trials, times by P, which is the probability of success, to the power of successes, times by 1 minus P, which is a failure, to the power of perfect, whatever the leftover is. Is that okay? It's literally what I've got down the board, but done generally. Now, sometimes you'll see 1 minus P written using Q, simply because it comes after P in the alphabet. Okay? So 1 minus P, the complement probability, you might see written as Q. So you might also see this. But it's literally what we're doing on the board there. Okay? In fact, we'll just zoom through the next couple. Okay? It's literally what we're doing here, and we're just multiplying everything together. Okay? So if you are given this situation here in general, in order to work out the probability of that many successes, this is how you would do it. Does that make sense to everyone? Yeah? So there you go. It's on the board there if you need it. Are there any questions about that? So I've just used X to represent the outcome on the board. I've used R to represent the number of successes on the board, and X to represent the number of successes on the screen. Yeah? But it's exactly the same idea.